This is a NEET 2013 question basing on photoelectric effect. The question says, for photoelectric emission from certain metal, the cutoff frequency is nu. Cutoff frequency is the minimum frequency of the incident photon so that photoelectric effect can happen. If the radiation of the frequency is too nu on the metal plate, what is the maximum possible velocity of the emitted electron? So it's very simple. This is to say that according to Einstein's photoelectric equation, the energy of the incident photon is used in two steps. First, to release the electron from the metal surface called work function. With the remaining energy of the photon, the electron moves with a certain kinetic energy. Energy can be written like h nu. Work function is h nu naught plus kinetic energy is half mv square. So h of nu minus nu naught is half mv square. Here incident frequency is 2 nu, threshold frequency is nu. So h of incident frequency is 2 nu, threshold frequency is nu, that is given as a cutoff frequency, equal to half mv square. So h nu equal to half mv square. 2h nu by m equal to v square. V equal to square root of 2h nu by m. So it's a very simple question basing on Einstein's photoelectric equation. Very basic question. Let's look at the next question. What is that? The work function of a metal A, B, C are respectively given for you as 1.92 electron volts, 2 electron volts and 5 electron volts. So what is work function? As I have told you here, according to Einstein's photoelectric equation, incident energy is work function plus kinetic energy, where work function is the minimum energy required to release the electron from the metal surface, h nu naught. That values are given for three different metals as 1.92, 2 and 5 electron volts. According to Einstein's photoelectric equation, the metals which can emit photoelectric effect with an incident wavelength of 4100 angstrom are, energy equal to h nu, that equal to hc by lambda. So if you substitute this Planck's constant c and lambda and get energy, if lambda is substituted in meters and Planck's constant and c, you will get energy in electron volts. But to get energy in electron volts, after substituting and converting, the final equation will be like this. This is the equation that we have derived mathematically in the playlist of the chapter. You can remember this equation if you have not gone to that chapter earlier, right? Otherwise you can just go through, substitute, calculate, you will get the same equation. Energy corresponds to 4100 angstrom. I am using this because incident wavelength is given in angstrom, is 124 by 41. So if you calculate that, it's approximately 3.1 electron volts. So energy of the photon that is striking the metal surface, this is the metal surface, this is the photon, is 3.1 electron volts. That's the available energy from the photon, 3.1 electron volts. So if the work function of the metal is more than 3.1 electron volts, it means to say available or incident energy is not sufficient to release the electron from the metal surface. Look at the data. Work function is given as 1.92 for one metal. This is 1.92, but photon has 3.1 electron volts. So photon with 3.1 electron volts will hit the metal surface. Metal surface absorbs 1.92 electron volts and release the electron from the metal surface. As 1.92 is less than 3.1, with the remaining energy, kinetic electron moves with a certain velocity. So photoelectric effect is quite possible with 1.92, with 2 also, because 2 is less than 3.1, photoelectric effect is possible. But look at the 5 electron volts. which is more than 3.1. Photon can give you only 3.1, but that metal has a work function of 5 electron volts, means to release electron from that metal surface you need 5 electron volts. But photon give you only 3.1, which is not sufficient to release the electron from the metal surface. So there is no photoelectric effect with C. There is photoelectric effect with A and B. That's the answer for the problem. That's how we have to solve that. Thank you for watching.